Hello everyone. Today I'm presenting my project demo for my course project, Fairness for Large Scaling Factor Phase Resolution. First, let's begin with question review. Let's review what is fairness in large scaling factor phase resolution. The large scaling factor means that the inputs of phase resolution models are of low quality and phase resolution models are becoming more dependent on the prior knowledge of phases. And when depending on prior knowledge, the models are very biased as the training data is usually biased. And this is a very good example of the bias phenomenon for phase resolution models. You can see that the scaling factor we use here is 32, which is very big, and the input image is very blurred and very low resolution. And so for these three models, we decide to generate or super resolute middle-aged white male. But the ground truth for the picture is actually a young white female. And this demonstrates that these models have a preference for the middle-aged white male, and of course they are biasing this uh, young white female. And this is the fairness problem for phase resolution. And my course project is focused on race bias in phase resolution. And the example I just show is about age and gender. But there are, of course, race bias in these models. And for we humans, we recognize people's ethnic according to people's facial components, such as the shape of eye, the shape of your nose, the shape of your lips, and the color of your eye. And of course, the color of skin is important, but usually the model won't mistake that. And large scaling factor face resolution models, they prefer facial components that more white. And this making faces lose their facial racial features. These are two examples that I generate. We can see that this picture, the ground truth is a black female, but after face resolution, the result in the middle, she looks like somewhere from Hawaii or in India. You can see that her lips are become thinner, her nose and thinner, and her eyes are all have colors, and these are all changing her racial feature. And the second example is an Asian young woman, and we can see from here that she's clearly Asian female and probably from Japan. And in the middle here, we can see that the shape of her nose and the shape and the color of her eyes changed a lot, so that she looks more of a white person than an Asian person. And this is racial bias in face superillusion models. And because the training datasets that are used in most superillusion models are containing much more white faces than faces from other ethnic groups. And they are like having like a 90% of white person. So the model's knowledge is very biased. And of course, the output is very biased. And this leads to the design part of my project. This is the overview for my design. I call it visual image correction structure. And here's basically 4 steps what I'm doing. First, I use selected face super resolution model to generate super resolution facial images. You can see here. We put some low definition facial images to this super resolution model, then we can have a super resolution facial images. Then I perform semantic segmentation on these super resolution facial images. Basically, after we scan these super resolution facial images, we put it into a segmentation model. And the segmentation is basically tell the computer which part is your nose, which part is your eyes, which part is your lips, and which part is your ears, and so on. And then we can have a mask for each facial component and tell the computer how the face actually look like. And then we send the segmentation mask for requirement. As I just say that the supervision model will likely to change the shape and the position of each facial component, and so we want to correct that. We want to fix that. So we then send the mask to the mask repairment model or mask fixing model, and we have a fixed or repaired mask. And this mask is more accurate than the original mask compared to the ground truth face. And then we use the repaired mask to correct the super resolution images with some facial image manipulation skills and or portrait editing skills, whatever. And then we can have a more accurate super resolution facial image, and this is could be more fair or more authentic for each group. Let's look at the facial image segmentation correction part, which is the core design of this project. And you can see basically in the red box here. And after segmentation, we have a mask. The mask is generated according to the super resolution facial images, which is not accurate. And we want to correct this mask a little bit so it can be more accurate. We can use that for later. So this is basically a pixel to pixel translation task. So I just select a normal UNet and change the output of the UNet to suit the segmentation input. You can see the model training details here. First, we put the ground truth images to the segmentation model, and we can have the ground truth mask. And then we put the super resolution facial images to the segmentation model again, and we can have some super resolution masks. And these two masks. We want to make the super resolution mask closer to the bounce mask possible, and so we put it into the mask repairment model, and the mask repairment model will generate a repaired mask, and in this process we use cross entropy loss to supervise if this repaired mask looks like the bounce mask. And the training dataset I'm using is FFHQ, and which is different from the test datasets, which we will come to later. And next part is segmentation guided face manipulation. And after we get accurate or repaired mask, I want to use this mask to fix or repair the super resolution facial images and with some technical face manipulation. And there's a lot of face manipulation skills. And of course, there are some learning based, but here I choose to use some basic vision techniques such as scaling, interpolation, filtering, and I use these techniques for each facial component individually. For example, if the repair mask tells us that your eyes are bigger than the original one, I will scale up your eyes and use some interpolation inside your eyes. And after this uh, operations, I will filtering around your eyes to make the borders less visible, to make the artifacts less visible. And if, for example, your nose is actually thinner than the resolution facial images, I will like scaling down your nose a little bit and interpolation around the nose and then filter around the nose to make artifact less visible. And for each facial components, including like eyes, eyeballs, ears, and nose, mouth, lips, I will always conduct I or conduct similar operations and to get a final super resolution facial image, which is more correct, more accurate. Next, I will show some results for my project. First is a label subdataset for celeb A. Celeb A is another dataset that used for face resolution, and because I already use FFHQ for the training, so I cannot use that for testing. So I choose delivery for test, and I have choose some pictures for each ethnic group. You can see here is 350 white and 420 black, 310 Asian, 500 Indian, and others. And to be specific, Indian and others include some like people from Middle Eastern and maybe Mexico, but they are not necessarily not white, but not that white, just to be clear. Next is some results for the face segmentation repairment. The supervision model I use here is GPen. It is one of the state-of-the-art models, especially when the scaling factor is large. And here's some accuracy are calculated for each mask in each group. And by accuracy, I mean that if the masks, if the one pixel from the mask is have the same uh, semantic group with the original or the ground truth mask, then I consider it the same and use you add all the correct pixels together and you and have it over the total pixels. So we have an accuracy. And to be clear that the background and the here are not considered while calculating this accuracy. We can see from the data that for each group, the accuracy for the segmentation have increased by around 2%. That's actually a lot because uh, some very minor change in the pixels will make the shape of each facial component looks very different. So I can say that after my repairment, the segmentation mask is more accurate than its original version. And here is a visualized result for the facial segmentation map repairment. And you can see here that actually the segmentation map is, or mask is telling you which component is which component. This is, on the left is the original picture, on the middle is the repair mask, and on the right is ground truth. The difference is not so obvious, but we can see that the repaired mask have thinner eyes and thinner eyeballs comparing to the original ones. So that makes this uh, mask more accurate, and also the shape of the nose is slightly different, and uh, that's basically what makes the mask repairment work, is this tiny component. Next is some results for the facial image correction. And in the first chart, you can see that displays some PSNR value. The PSNR value is very common in the computer vision, and the higher the PSNR value is, the better the quality the images have. You can see that the quality after repairment is, so after the correction is almost stays the same. It has a it's slightly increased, but not so obvious. But for the second chart, displays the FID score. The FID score, the lower the FID score is, the closer the generated images are to the real images. You can see that there's a very obvious drop in FID score, which means that after repairment, these pictures are more like the ground truth than their original version. And also you can see that the difference between each group in aspect of FID score also drops very obvious. This also proves that my arguments for the the bias comes from the changing of shape of each facial component is right, and it's also very incredible that you can decrease this much. Next we have here is visualize results for facial image manipulation or facial image correction. You can see on the middle is manipulated result, on the left is original result, the original super resolution facial image, and on the right is ground truth image. And there's no very obvious visual difference in these two pictures, but we can see that for the eye part, it's apparently a little thinner. I don't know. And for the nose, it's also a little thinner, which is closer to the ground truth image, and makes the manipulated or repaired image more close to the ground truth image. Finally, I have some discussion about my project here. So the first one is fine-grained filtering. So as I mentioned, for the facial image manipulation part, I use some basic vision skills, and I haven't really designed a very uh, specific filter for that part. So so I will introduce some artifacts after the manipulation. That's the main reason for the PSNR not being higher. Actually could be higher. So if I can design a fine-grained filtering, the PSNR will be better, and maybe the FID can be lower. And the second is better designed facial segmentation repairment model. So for this cross project, I just implement a plain unit, which is very straightforward. But a unit can of course be adequate for this task, but you can see that the improvement for the accuracy is like 2%, but I think there is still a large room for improvement if we can add some layers or some new design to this part. I think the repaired facial masks will be better. And the third one is color repairment. I want to find a efficient way to repair the color for each image. You can see from the examples just now, the color of iris is are incorrect, but I haven't really figured out how to do this. But if we can fix this, we can solve this problem. The PSNR and the FID will further improve. And the last one is learning-based face manipulation model. And because I use some basic physical vision techniques and maybe some learning-based facial image manipulation model will perform better than what I implement here. And that's all for today's presentation. Thank you.